All right, good morning. I'm Tom Curran. I work on the Xilinx technical marketing team at Avnet. And today I'll show you the demo we have running on the Avnet Zynq Mini ITX platform for showing partial reconfiguration of the Zynq PL. It's a software-defined radio application demo using the Avnet Zynq Mini ITX hardware platform and the analog devices FM Comms 2 FMC module that uses their AD9361 radio chip. So the demo is to show partial reconfiguration of the Zynq PL. And the design they have is one partition that they set up for reconfiguration and three different modules they set up for reconfiguration. One is a default module that's simply data in, data out, or data out, data back in on a loopback. Second module is a built-in self-test. And third module is QPSK modulation of transmit data. And here right now we show right now is running the QPSK modulation, and I have the software application already set up, and it's a simple software application that runs so I can reconfigure simply by telling the application I want to go back to looking at the default logic, and that's simply a sine wave, right? What goes out, what comes back in. Then I can reconfigure for the built-in self-test, and this is going to show a constant pattern test, transmit and receive test. From there we can change it again to the QPSK modulation.
Yeah, so that's actually doing FaceTime.
So that's all happening within the reconfigurable logic.
And that's all happening within a region of the reconfigurable logic. So it shows you that the system continues to run. So you're doing an update, a design change on the fly.
Right.
Right. And if you looked closely, you would be able to see the done light blink as you reconfigure.
This is not depth.
Because that happens very quickly.
It sure does. I'm not sure I caught it. Here, let's get zoomed in really close. Okay, go ahead.
Your eyes will turn red.
I'm not sure this camera's seeing it, but
Yeah.
it blinked for less than a second.
Yes, it happens very quickly.
Okay.
And that all happens because Linux takes care of, there's two commands that run. First is to tell the virtual file system and to tell the dev-c, the dev-config device, that you're going to partially reconfigure. And the second is to actually write the bit stream to the PL. And that happens by the dev-c takes care of the DMA transactions to fetch the bit stream from the file system, send it across to DDR3 using DMA, and then into the AXI PCAP bridge into the PL to reconfigure the region of the PL.
Okay, so you've got this thing running Linux, you said?
Yes.
And I see you got a free RTOS block diagram down there. That's a different demo?
That's a different demo we're showing today, and we can show that simply by shutting this demo down and changing out the SD card.
Yeah.
The man that runs that demo is in here.
That's okay.
So what that demo is, it's showing an AMP configuration of Linux running asymmetrical processing. So it's Linux running on one of the ARM cores and FreeRTOS running on the other ARM core.
And why would you do that?
A lot of times you need an RTOS. Customers want an RTOS to handle some data path or something going on in their system that they need to keep control and keep track of in real time. And they use Linux for, say, user interface or something that requires more throughput but not determinism. So they want the best of both worlds. And having two ARM cores allows them to do that. Use FreeRTOS for what you have to do quickly and in real time, and use Linux for what you don't have to do in real time.
Okay, thanks.
Thank you.